Hey everyone, and welcome to This Explainer. Have you ever paused in a crowded airport or maybe gotten stuck waiting at a massive train crossing and just wondered how all those moving pieces actually coordinate without collapsing into total chaos? Well, it turns out there is this incredibly powerful, completely hidden layer of mathematics that quietly runs the modern world. So today, we're going to demystify network models. We're going to literally pop the hood on global logistics to see the abstract equations that make absolutely sure your packages arrive on time, your flights actually take off, and your water keeps flowing. And we're launching straight into the high stakes today, because the math we're talking about, it's definitely not just some dusty academic exercise.
More than $500 million. Yeah, you heard that right, $500 million. That is the kind of massive bottom-line impact we are talking about here. Long before we even touch the mathematical theories today, I really want to anchor our discussion in this reality. This staggering number was achieved by the Canadian Pacific Railway. But how on earth did they unlock $500 million in savings? Well, they didn't do it by simply laying down more track or buying faster trains. No way. They did it by entirely rethinking their operations through the lens of network optimization.
Okay, let's dive into this. Prior to their massive operational overhaul, the Canadian Pacific Railway had this surprisingly simple but highly flawed policy. They would only run their trains after a sufficient level of freight was attained. Basically, you wait until the train is full and then you send it. Sounds logical enough, right? But actually, this policy resulted in wildly unreliable delivery times and just extremely poor customer service. To fix it, they created what they called an integrated operating plan, literally treating their entire massive fleet of trains, railcars, and crews as one giant mathematical puzzle. By using shortest path problems over a directed graph, they created a precise blocking and train plan. They completely optimized their scheduling, slashed transit times, balanced out workloads, and ended up saving over $170 million in just half a year, which eventually snowballed to exceed $500 million in savings. Crazy, right?
So here's our roadmap for this explainer. 1. Decoding network models. 2. The minimal spanning tree. 3. The shortest route technique. 4. The maximal flow technique. And finally, number 5, real-world optimization.
All right, part 1, decoding network models, the secret language of logistics.
Let's start with the basic grammar of network diagrams. No matter how incredibly complex a logistical problem might be, it can almost always be simplified down into two really abstract elements: nodes and branches. Think of nodes as simply points or circles representing actual physical locations, like a warehouse, an airport, or an entire city. Branches, which are sometimes called arcs, are the lines connecting those nodes. They represent the actual paths, the physical roads, the railway lines, or the telephone wires jumping between those physical locations. By stripping away all the messy, complicated real-world details and just drawing circles and lines, we can step back and let the math take over.
Now, what's really interesting about this is how we can start adding rules to those basic shapes. Take an undirected system, for example. Imagine a two-way street where you can just travel back and forth between the nodes totally freely. But then, compare that to a directed path. You'll notice these have arrows on the branches, which signifies a strict one-way system. You can travel from node A to node B for sure, but you absolutely cannot travel backwards from B to A along that exact same path. It seems super simple, but this tiny visual distinction is absolutely vital when we're trying to optimize something like a complicated municipal water system or a one-way downtown traffic grid.
Moving right along to part 2, the minimal spanning tree, connecting everything cheaply.
The whole goal of the minimal spanning tree technique is to find a path through a network that connects every single point while minimizing the total overall distance. It is basically an exercise in absolute ruthless efficiency where nothing is wasted, and it follows a surprisingly methodical step-by-step algorithm. Step 1, you just arbitrarily select any node in the network to start. Step 2, you connect that node to the absolute nearest node, keeping the distance as short as possible. Step 3, looking at the little cluster of nodes you've now connected, you find the closest unconnected node and branch out to that one. Step 4, you just repeat this process over and over, growing your tree branch by branch until every single node is hooked up to the network.
To bridge this math theory to a real-world application, let's look at the Lauderdale Construction Company. So they were developing a housing project with exactly 8 houses and needed to figure out the absolute least expensive way to provide water and power to every single one. By applying the minimal spanning tree algorithm, they evaluated the distances between all the houses, which are our nodes, and mapped out the branches. Instead of just kind of guessing where things should go, the math dictated exactly where to dig the trenches. By sequentially connecting the nearest unconnected nodes, they solved the puzzle using the absolute minimum amount of material, exactly 1,600 feet of pipe. literally drawing specific lines on a page, translated to massive immediate physical construction savings.
All right, part 3, the shortest route technique, finding the fastest path. And this brilliantly illustrates what an incredibly complex routing problem actually looks like on paper, before the math comes in to save the day. Imagine we have an origin node marked O and a final destination node marked T. Right in the middle, there's this crazy complex spiderweb of potential paths bouncing through nodes A, B, C, D, and E, and each little jump has a different assigned distance or travel time. If you're a delivery driver or even a network data packet zipping through the internet, you can't just guess which way is fastest. You need a systematic, foolproof way to untangle this web. So the algorithm methodically steps through all these options to find the definitive answer. It doesn't look at the whole map at once and freak out. It breaks it down. At step 1, starting at our origin O, it evaluates the nearest node, finding A at a distance of 40. Then, from its newly solved nodes O and A, it evaluates the next closest connections, finding nodes B and C. It systematically keeps track of the running total distance involved at every single step, constantly, always selecting the path of least resistance. Evaluating paths through D and E, it progressively eliminates any routes that are taking too long. Finally, it arrives at the destination T, definitively proving that the absolute shortest path is exactly 160 miles. No guesswork, no estimating, just pure optimization.
On to part 4, the maximal flow technique, maximizing throughput.
The maximal flow technique is defined exactly as it sounds. It's an algorithm used for finding the absolute maximum flow of any quantity or substance that can effectively pass through a network system. So contrast this with the previous techniques we just talked about. We literally no longer care about finding the shortest distance. This algorithm is entirely about capacity. How much stuff can we forcefully push through these branches before the system bottlenecks or totally breaks down?
To firmly ground this super abstract concept, let's look at some rapid-fire, real-world applications of maximal flow. Think about city planners designing downtown road systems in Waukesha, Wisconsin. They actually use maximal flow networks to determine exactly how many cars can pass through a one-way grid during rush hour without causing a total gridlock. Or think back to our railway examples. Planners use this exact math to calculate the maximum number of scheduled freight trains that can safely operate on a track, especially when a faster passenger train might suddenly need to overtake them. It's also used heavily in civil engineering to maximize the flow of water through municipal pipes of varying diameters. Basically, it's all about finding the absolute physical limit of a system.
And that brings us to part 5, real-world optimization, the United Airlines story.
So the crucial point is the jaw-dropping contrast achieved here. Before applying these really advanced network models, United Airlines was seriously struggling with crippling flight delays, terrible aircraft shortages, and as you'd expect, really poor customer service. But then they realized that scheduling aircraft wasn't just a basic logistical chore, it was actually a highly complex network problem. They began solving their delay problems for each airport separately by treating them as a minimum cost flow network problem. They mapped out flights, aircraft availability, and transit times as nodes and branches. The math then determined exactly which flights to delay or cancel to cause the absolute least amount of disruption across their entire global network. And the after picture? It's astonishing. By applying this math, they reduced flight delays by an incredible 50%. And in less than a year, this one study saved United Airlines over $500 million in delay costs alone. From the exact length of water pipes laid under a brand new neighborhood, to the freight trains moving across the Canadian wilderness, to the precise, down-to-the-minute scheduling of your next commercial flight, network optimization models are quietly running the world. They completely eliminate waste, they save literal billions of dollars, and they keep our modern society moving forward. So as we wrap up this explainer, I'll leave you with this final provocative thought. Take a look around your city today. What hidden networks are running your own life without you even noticing? Thank you so much for joining me, and hey, keep looking for the math hidden in plain sight.